All right, so I'm out today, so I'm going to walk you through the notes I would have given if I were there. Feel free to use this or feel free to go on and do it as a student paste, whatever you want. This is just here for you if you want. Okay, so today we're going to look at moving up and slowing down, which is the rocket's second phase. And we're going to look at a second kinematic equation, V final squared equals V initial squared plus 2AX. So our learning objectives. Students will be able to calculate the maximum height a rocket can reach after the rockets have stopped firing. All right, so we've seen this graphic before. This is the total flight of Freedom 7, the whole 15 minutes it went from up to down. And today we're going to focus on from 2 minutes and 22 seconds to 5 minutes and 14 seconds. This is our phase 2, and this is where it is moving up and slowing down. All right, so we need information from phase 1, which is getting up to speed. Our engines are on and firing. And once they stop firing, that's when we enter phase 2. So we know from our phase 1, our initial velocity is 0 because it was just sitting on the landing pad. Our final velocity is 2,200 meters per second. And we know this because to get into suborbital flight, you have to be going that fast. We calculated the acceleration last time using our kinematic equation 1, and that was 15.5 meters per second squared. And the time period over which this happened was 142 seconds. And we're going to come back to this graphic the next time we do notes, filling in phase 2, and then doing calculations for phase 3. All right, Freedom 7, moving up and slowing down. So at 2 minutes and 22 seconds, the rockets on Freedom 7 stop firing, and we want to draw the forces or the free body diagram on the capsule. All right, so what we have here is on the capsule before this, of course, it's a terrible arrow. Before this, of course, we had force due to thrust and force due to gravity. Once the engines turn off, it's only force due to gravity or force due to weight. Now it says determine the acceleration of the capsule. Well, to determine the acceleration, we again need to know which way the force is going, or the net force is going. And here we know we have force due to gravity down. There's nothing up, so my net force has to be down as well. So my acceleration is always in the same direction as my force. So my acceleration is also directed down. Now it says describe the velocity of the capsule, direction, and how it's changing. All right, so again, we know we've got force due to gravity pulling down. We know we have our acceleration is directed down, but we know it was speeding up until it got to its highest speed right before the engines turned off, and that's our initial velocity for phase 1. So our V initial is 2,200 meters per second. And then we know in the end, our final velocity is 0. So velocity is directed up, but it's decreasing. And anytime I have velocity and acceleration opposite, we know we are slowing down. So we know these two are opposite. So we know here that we are slowing down. We are slowing down there. All right, so let's look at our kinematic equation 2. V final, of course, is our final velocity in meters per second. Then we have V initial, which is our initial velocity in meters per second. A is the acceleration in meters per second squared. And please keep in mind it is second squared because acceleration is the change in rate of velocity. And then we have x, which is distance in meters. And one thing I want you to notice here is there is no time in this equation, which is different because the last one did have time. All right, so free fall acceleration. This is acceleration due to gravity or acceleration when the only force acting on the object is gravity. When the only force acting on an object is gravity, the acceleration will be negative 9.8 meters per second squared. And of course, this is only on Earth. It's different on different planets. On the moon, it's negative 1.6 meters per second squared. On Mars, it's 3.7 meters per second squared. And on Jupiter, it's negative 24.5 meters per second squared. All right, so here's Miss Tan walking through the two videos. So I'm not going to go through these because she is going to, and you guys can watch them just in the Pear Deck. Okay, so Freedom 7 began from rest. So we need to figure out what from rest means. So this question is talking about phase 1, where it's sitting on the launch pad and then accelerating up to its final velocity. And so for this one, this is going to be our initial velocity is from rest. The next highlighted thing is it accelerated at 15.5 meters per second squared. And there's two ways we can tell this is acceleration here. We can look at the units on 15.5, which is meters per second squared, and that matches acceleration. And then it also says and accelerated at. So there's two clues that this is both acceleration. The next number I'm looking at is 2,200 meters per second. How high did the rocket go during this acceleration? So this, of course, is our final velocity, and we know this in two ways. One, there's meters per second, and we've already decided our initial velocity was 0, and it says it accelerates to a final velocity of 2,200 meters per second. So that one is definitely our final velocity. And then here we've got which variable are you solving for? And I can just read the last sentence. How high did the rocket go during this acceleration? So I'm looking for distance here. All right. So now we're talking about 2,200 to rest. So this is phase 2, where the rockets are off and it's just coasting up and slowing down. So Freedom 7 decelerated from 2,200 meters per second to rest. So the 22 meters per second is my initial velocity for phase 2. Because again, the end velocity for phase 1 is the initial velocity for phase 2. So in phase 1, it went from 0 to 2,200. In phase 2, it actually does the opposite. It goes from 2,200 to rest. So now, of course, we're going to look at rest, which is our final velocity for phase 2. At the top, it pauses for a second before it starts falling. Now we're looking at negative 9.8 meters per second squared. And again, there's two ways to look at this to determine what this one is. Its units are meters per second squared, which again is acceleration, or you can read the full sentence with an acceleration due to gravity of negative 9.8. So this guy is acceleration, no matter which way you look at it. And then here we have Freedom 7 decelerated from 2,200 meters per second to rest during an acceleration of negative 9.8 in the second phase. How much higher did the spacecraft go during this deceleration? So again, we're looking at distance here. All right, so my total height of Freedom 7, it went 156,000 in the phase 1, 247,000 in phase 2. So the total height is 403,000 meters. So pretty high up there. All right, so here's our closing question. In order to reach low Earth orbit, a rocket must have a velocity of at least 7,800 meters per second. If the rocket started from rest and reached a height of 500,000 meters, what must the acceleration of the rocket be? Okay, so again, we're going to use our new equation. Let me make that a little smaller. All right, so we're going to use V final squared equals V initial squared plus 2 plus 2ax. So now let's read our problem and decide what all the variables are. The rocket must reach a velocity of at least 7,800 meters. So meters per second, rather. That's our final velocity. So let's plug that in. 7,800 squared equals, the rocket starts from rest, so that's my initial velocity, 0 squared plus 2. Okay, and we don't know the acceleration because they're asking for that. What's the acceleration? So I'm just going to put an A in there. And then it says it reaches a height of 500 meters, or 500,000 meters, rather. All right, I'm not going to solve this here. Solve it, and you're all set for today. Have a good one.